Hey everybody, welcome to the DeCal. Today's Wednesday. I believe it's we're week 6. Thank you everybody for coming to lecture if you came in person. If you could, please go ahead and turn on your camera. You don't have to if you don't want to, but it's always encouraged and it helps make it feel a little bit more like a real classroom. Yeah, and also the attendance form is on the first slide for those watching. And for those just trickling in, here's the attendance form in the chat. So you could either click on the link in the chat, or if you're watching it asynchronously, you can copy and paste the link from the slides. Cool. Yeah, let's go ahead and get started then. So today's Wednesday. I hope everybody likes my office GIF because The Office is the best show ever. Let's go and get started. So we got some announcements. Fill out the quiz survey on B's courses. So far, I've only seen, I think, 4 people fill it out. So please do that. We need you to do that before Friday. If you don't do that before Friday, we can't put you in a group /partner /working by yourself on your final project, and it's going to slow everybody down. We want to make sure you have lots and lots of time to do these final projects. The final project is the most important part of this entire course. It's what you actually have to show for. And I want you to walk away with something really badass to show, whether that be your colleagues, maybe that be an application to work at a summer program, maybe that is just trying to get a cold email response from a postdoc. If they see you have at least some really cool final project it's like a lot of coding, I think it would make your application look a lot stronger. So we want to make sure you have a great final project. That's going to be the thing that we really want you to do well on. So please get that done before Friday so we can start putting you in your groups right away. Homework 4 was just due. I hope it wasn't too bad. Actually, I had somebody come to my office hours today. I was so happy about that. That really made my day. And homework 5 will be released tonight. That's going to be regarding numerical differentiation, integration, which is what we're talking about today, as well as root finding and curve fitting. So it's kind of a packed homework. It's a lot of like the professional science tools that you will need, kind of like enveloped into one assignment. So it'll be a lot. It'll probably be just as much as this homework that was just due, if not a little bit more. So just be on the lookout for that. It'll be released tonight. Cool. Yeah. I guess I should say, is there any questions before we get into a recap? Okay. If there is anything, please feel free to put it in the chat. Don't hesitate. I'm happy to answer them. I have my chat window open. Okay, let's get into recap before we go into our breakout rooms. So on Monday, we talked about curve fitting and root finding pretty in depth. We talked about the several different functions. The main curve fitting functions that we use you'll ever need to use is np.polyfit and then the curve fit function from the Scipy library. Both of those are really useful. Polyfit, I'm not going to describe the differences. I'm going to let you talk about that in your breakout room. But we talked about those and what curve fitting is. It's fitting a model to a big old set of data, right? And you want to figure out the best fit to that model, and you use a curve fitting function to do that. So I have some questions here for you. Namely, what are the differences between curve fitting, or using the curve fit function, and the np.polyfit function? And then what is the thing that curve fit is minimizing to determine the best fit to the data? We talked about it a little bit. It was kind of like a point that I asked a question about last time. I want to make sure you, at least if somebody asks you what a curve fit does, I want you to be able to tell them what it is it's actually trying to do. So yeah, we're going to go into breakout rooms for maybe 5 minutes or so. And yeah, I'll let you guys answer this question. So I'm going to go ahead and pause the. Cool. So we just finished our breakout rooms. Would anybody like to volunteer to answer the first question, either in the chat or verbally? Okay, I'll start off with the first question then, and hopefully somebody can answer the second question. So what are the differences between curve fit and np.polyfit? Remember poly, short for polynomial fit, right? So very similar to like a Desmos calculator, or like, or not Desmos, but like a TI graphing calculator. The way they plot lots of functions is actually by approximating it with polynomials, polynomial expansions. So you can, if you have any like smooth continuous function, usually you can approximate it by a series of lots and lots of polynomials. Or like an n degree polynomial. And so if you have a specific function that's smooth and continuous, and it could be fitted by a polynomial, then you can use np.polyfit. Think of it almost like a Taylor expansion or something like that. And then curve fit takes in any function or I guess the model function that you're using to model or like to curve fit to your data isn't just a polynomial. It's actually any function. You can specify any function in the curve fit function to try and model your data with. So that could be a Gaussian, like a peak. That could be something crazy. I can't think of like really complicated functions. It could be series of sines and cosines. It could be, yeah, it could be anything. There's tons of functions out there that are crazy and wacky, and you can use your curve fit, and it can have as many variables as it wants, and as many parameters as it needs. So that is like kind of like curve fit, I would say, is like the most versatile version of being able to fit a model to some data. There's a lot of freedom you have with it and a lot of versatility, but it's not necessarily as easy as like the np.polyfit to use. It's a little bit more involved. Okay, can somebody take over for that second question for me, please?
Yeah, I'm sorry. Yeah, so that's chi. It's chi, which is like minimizing the distance between the plot and the actual, like, the curve.
Exactly, that's exactly right. So technically it's chi squared, but I mean chi squared doesn't really matter. And yeah, exactly like you said, you're adding up the difference between all of the data points and your model, and you're trying to minimize that the total sum of all those differences, and that gives you your chi-squared value. And if anybody has taken 5BL, 5CL, your labs, most labs, including like 111A and so on, something you're going to have to do is maybe curve fit your data to or your model, like a theoretical model to your data. And you need to calculate chi-squared, because that tells somebody, hey, my curve fits this data this well. And if you have a really bad chi-squared value that's really large, obviously your data is crap and your model's crap, and you should take your data again or something like that. So yeah, that's the most important thing about the curve fit function, like to keep in mind like what it's doing. It's doing that chi-squared minimization. It's trying to find the minimum chi-squared value based off of moving the parameters around of your model. Great, cool. So that's our recap. Hopefully that gets your brain flowing, because today we're going to talk about differentiation and integration, specifically in Python, and numerical integration differentiation. So this is very useful, just like everything else we talk about, but this probably has the most application to like functional programming, using lots of functions and like models and stuff like that. If you need to calculate like a derivative of whatever theoretical function you may have, this is kind of your go-to. So we're going to use some packages just like we always do. This time we're using the scipy.misc or miscellaneous library, and we're just going to import a specific function from there. We're going to import the derivative function. So from scipy.misc, we're going to import the derivative function. That's how you write it. And then the way you use this derivative function, it's spelled out on the slides, but just for verbal context, func is the first argument. That should be that's the function you want to integrate. So it could be x squared, it could be x cubed, it could be x plus x squared, it could be, you name it, the exponential of negative x, it doesn't matter. And then the point which you want to evaluate your derivative at, that's x naught. So this is kind of like a good graphic label of like, or a good plot of like what's going on. X naught would be like the little region in here where you want to evaluate your derivative, or like at x. Dx is the spacing, and then order of differentiation, meaning like, do you want the first order derivative, second order derivative, third order derivative, how many times do you want to differentiate your data or your line or your model or whatever. Needless to say, the smaller the spacing, the more accurate your derivative is going to be, or the more precise it'll be. The bigger your spacing, the less accurate you get, and that just comes from like the definition here, right? If your delta x is large, it's not the limit anymore, and it becomes less and less accurate. The smaller your delta x gets, the closer to the limit you reach. So it makes sense that dx, the smaller that gets, better. But the trade-off is the smaller your dx, the more time and more numerical power it requires to fill out that operation, right? So just it's good to find like a good balance, and I think that'll come with doing your homework assignments. Cool. So there's two ways to define a function that you put inside of your derivative function, like one of which is the normal way with the def statement that we talked about, where you define a function with your def statement, you have a name, func, it takes in a variable x, it returns like whatever quantity you want. So in this case, the function is x squared plus x. That's like what we're doing. And then the other way to do it, which is the quick and dirty way, and honestly, you probably shouldn't do this for clarity of what you're actually, like if you want to keep your code clear, I highly recommend staying with the normal way. But if it's quick and dirty, like you just want to calculate the derivative of some function or whatever, then you can just do a lambda statement where you say, in like, if you don't care about this function ever again, you just need it for like this in particular, or this particular line of code, then you could say lambda x colon x squared plus x. And this is definitely different syntax. I believe we touched on it very lightly several weeks ago. I think it was like week 3. I think it was Emily's lecture, if I remember right, where we taught like we define it in the following. A lambda function is like something that Python, it's like a built-in feature of Python, and it's very shorthand. The way the syntax works, lambda x is your variable. Everything before any name before the colon means a variable, or in between lambda and the colon is a variable. If you had a multivariable function, it'd be x comma y colon. That's how you would define multiple variables or input variables. The same thing as putting x comma y in your def statement here. And then the colon tells Python, hey, everything past this line or past this colon is going to be a part like what it returns. So in this case, x squared plus x is the return value for a given x. Usually you don't want, like this is like a one-line function. They should be very, very simplistic. If you need multiple lines and like lots of constants and stuff, highly do not recommend the lambda function. Stick with the def function. But just in case you come across it, this is what that lambda x is, just to remind you that is the same thing as defining a function, but it's just a shorthand that is sometimes used. And then we're just evaluating at x equals 16 or x equals 17. That's like the x naught we're evaluating our derivative at. And then I'm going to set my dx equal to 10 to the negative 6. It's a pretty small step size. And I'm just taking the first derivative. And that'll spit out a value. Ooh, moving too fast. That'll spit out a given value. We can do a little bit of a demo at the end if we would like to see that. But that is how you apply a derivative at a specific point. So you can imagine if you need to apply the derivative at a list of points for every value in an array, for example, then you might need to use a for loop, or if you're using arrays, you can just put an array in there. And I'll show how to do that at the end of this lecture when we have some demo time. But I want to get into numerical integration. That was all different, like differentiation. It's pretty simple. It's just like a Scipy function that's like you just need to know how to use. Nothing too crazy there. I mean, you could calculate it like good old fashioned way using this definition here and calculate derivatives yourself. That's kind of a pain in the butt. I wouldn't want to do that, and I would rather just do something that other people have done, or like use something that other people have made that's probably a lot more efficient than whatever I could code. So that's why we use the derivative function from Scipy. But you could code it yourself. In fact, you can code it using like a centered method, a left method, or a right method, if throwing back all the way to your like early calculus classes. But yeah, not super important. Is there any questions about the derivative function before we move on to integration? Cool. I didn't expect there to be many questions. So let's go ahead and go into integration. So might remember, how do you do a numerical integration? Well, when you first learn calculus, you learn that any curve can be approximated by or the area under any curve can be approximated by adding up tons of little rectangles, right? That get smaller and smaller and smaller in width, and you can add lots and lots and lots of them, and then eventually you can actually approximate the curve, the area under the curve itself if you have enough of those little rectangles. And then you kind of learn, hey, well, there's not just the rectangles. Why don't we use another shape like a trapezoid? That might be even better because then you can have like an angled tip and you lose a lot less area. And so there's like the trapezoidal rule. Then there's like left and right and centered Riemann sums where you specify the height of your box or your little differential box. Yeah, that's all fun and dandy. Not super important though because there's a lot better ways to do numerically. That's qualitatively what's going on. If you want some real cutting edge ways of integrating, I recommend we use Simpson's rule or Gaussian quadrature. Now I could explain this to you. Well, I'd be lying. I can't explain this to you because I don't know how either of these really work that well. Simpson's rule is something to do with like polynomials, continuous functions. It's not fun. Gaussian quadrature is very complicated. Like if you look at the wiki page, which I linked, so if you want to go to the PDF and click on the link, you can go check it out. It's very complicated. I remember sitting through a Physics 77 lecture for 2 hours and having no clue what the heck he was talking about. All you need to know is that it's the most accurate. Gaussian quadrature is the best one, hence the meme. Definitely, we always use Gaussian quadrature. That's kind of like what's rocking in any like SciPy function that you use for integration is Gaussian quadrature. To my understanding, I believe it's like allowing, I don't know, I'm not even going to bother. Read the wiki page if you're really curious. It's a lot of abstract math that I couldn't care less for. Cool. So I have a little demo. Let's just go ahead and use something that we know, some basic while loop. And we're going to like actually do a little bit of integration of some function. So if you remember, this is kind of like the definition of a Riemann sum, right? You have an integral from a to b. That's like of f of x dx. Well, hey, the limit as n goes to infinity of these little like f of x evaluated at some x sub I times the differential width. That'll give you the area under the curve. And you define delta x by b minus a over n. So if you make n really, really big, henceforth your delta x should be really, really small. And you can add them all up. And we're just going to literally code this exact line. And I have a little bit of, oh no, I need to exit out of this slide. I have a notebook just ready to go, I think. Yeah, cool. So we can do a little bit of our while loop integration example. Now, so let's just go ahead and code it. We're gonna import numpy as np, okay, and then we're gonna define a function. I'm just gonna define a while loop integration function. We'll call it while int, and it's gonna take in 3 variables. We're gonna call it a, b, dx. A and b are the bounds. Dx is the differential width that I want. This could have been n, but I just prefer to use a dx because it makes more sense to me. And this is just going to be a simple function that evaluates some function, the integral of some function between 2 bounds. So how do we start? Well, we should start by defining a variable x. That's going to keep track of where our x position is. And we're going to set that equal to the initial bounds. That's a, right? So if x is equal to a, that's starting at the farthest left point where your bound might be 1. A is 1. And then we're going to start with the value of the area under the integral. This could also be called area. Actually, let's define it as area. I like that better. So the area starts off as 0 at x equals a, right? It should start off as 0. You don't have any pre-existing area in your function. And now we're going to do a while loop. And the way we're going to do it, you might recognize this kind of format. We're going to say that while x is less than b, we're going to go ahead and add up all these areas under the curve. And we're going to do them by, I'm just going to do it with rectangles, but if you wanted, you can go gung-ho with it. You could define trapezoids or circles, I don't know, whatever you were in the mood for. So then I'm just going to say y is equal to whatever function I want. So in this case, I'm kind of in the mood to do like x cubed. So then I think I'm going to set area equal to area plus y times dx. And so what that's doing, also, actually, really quick, can everybody clearly see what the text says? Like, is it clear for everybody before I keep going? Okay, cool. So in our while loop, what we have is x is less than b, we're going to calculate some value y equals x cubed, and that's literally taking like that's plugging in f of x at whatever x is. In this case, x is equal to a. So if a was 1, this would be 1 cubed. That's y. That's our y value. And then I'm going to say that the area is equal to whatever the area was before. That's area is equal to 0. We start off with no area in the beginning. And we add whatever that height is times the differential width. So this is base times height of your little rectangle. And then we definitely need to increment, right? Because if you don't have some way of incrementing your while loop, you're going to get stuck in an infinite loop, and you definitely don't want to do that. So we're going to say x is equal to x plus dx. And then that should be everything we need, actually. And then once you're done with all that, it will just return the area. And so we're incrementing the area with every single rectangle. And then after we calculate that area and we add it to whatever the value was before, then you just go ahead and you increment that x by dx, right? So if dx is 0.01 and x starts off at 1, because the bound was 1 at a, it goes all the way until it hits b, and then it returns the area calculated by summing all those little bits. Cool. So that's our function. Let's go ahead. Actually, for neatness sake, we're going to do truncate this a little bit just because I want to make it look pretty. Instead of writing this syntax, area is equal to area plus this, we can literally just go ahead and write this syntax instead, where we say area plus equals y times dx. That's the exact same thing. It's just shorthand notation, and it kind of looks shorter and cleaner. We're going to do the same thing with x. So it's plus equals here. So we have area. Every time you're going to add y times dx to the area. That's just what you're doing. You're adding that every time. Same thing with the x. You're just adding dx every time. Cool. Now we're there. We can run it. So I'm going to say, let's go ahead and evaluate this from -2 to 2. And we'll start with a kind of a large dx. We'll start with 0.1. And what you should get is a problem, right? Because it should be 0. That's because, I mean, it's pretty crappily approximated, right? 0.1 width is huge. If the bounds go from -2 to 2, that's literally like a 10th, a 20th, a 30th, like a 40th of the entire thing. Like that's like, I don't know, that's not very much. So you could just add, or that is a lot of width. So we can make it smaller and smaller until eventually it starts getting small. Like now it's 10 to the -12. That's pretty small. And I believe if I add like a couple more zeros, the more zeros I add, the finer it gets. It starts taking longer, starts fluctuating. But regardless, the more zeros you add, it should be getting closer to 0, but it starts taking a lot longer. Hence the runtime. Actually, this might break my computer, so I'm just going to go ahead and stop it. But regardless, oh, yeah, that gives you the point. And so that's why, I mean, like that's like basics of how to integrate or how to like actually code up your own integral solver, right? But obviously there's a lot of problems with it. Like it's not very accurate, first and foremost. I mean, 10 to the -7, 10 to the -12 or whatever, that's great and all. But I mean, if you used like the actual integrate functions available to you from another library from people that really know what they're doing, it'll give you 0 exact, or like 0 times 10 to the -100 or something. It'd be like spot on. So we're going to actually go ahead and rely on other people's integration methods instead of our own. So I'm just going to go back to lecture slides. So that was like a rough and dirty version of integrating with our own functions, like writing our own integration. But how do you do it, or like how do you use somebody else's functions? Well, you're going to need to use scipy.integrate, which is a library. Scipy library is huge. There's lots of sub libraries in it. We're going to use scipy.integrate. the little integration library they have. And we're gonna import it as an alias. So import scipy.integrate as integrate. That's just like saying, okay, I want every function available in this library at my disposal, and I'm going to, like, every time I need to call it, I'm going to do integrate dot whatever the name is. So numerical integration is super important in all of physics and astronomy, like I said before. And yeah, cool. So let's go ahead and do it. There's all these functions available to you. They're not super important, like all of them. A lot of them are kind of meh. I starred ones that are kind of like useful that you would probably need. Quad, I think, is the best one. This is Gaussian Quadrature. What I said. I can't really think of a time that you're not going to want to use Gaussian Quadrature. That's the method I talked about a little earlier. Don't worry about how it works. Just know how to use the function. It'll give you the most accurate area. You'll explore in your homework several of them. I think you explore like quadrature, you explore like trapezoidal, you explore like Simpson's rule, you explore, I think, rectangles or whatever. There's like one that's just straight up rectangles. And you'll see that Gaussian Quadrature is like far better than all of them, but that's for a homework assignment. So yeah, this is the one we're gonna use. And you just import the quad function. There's lots of different ways to import. You could have, like, if we use the syntax we used a couple slides before import scipy.integrate as integrate, then all you would need to do is say integrate dot quad. But in this case, like, I believe you could do it any way you want. There's from scipy.integrate import the quad functions. In this case, I literally am just telling the computer, hey, I only want this quadrature function. Don't give me anything else. And then I'm just using it. But there's lots of ways to skin a cat. So don't worry about it. You can use whatever you want. In this case, or however you want to import the function. You should definitely be using the quadrature function though. It's pretty simple, straightforward. The function that you want to integrate, and then, or like that's the func argument. A is the lower bound, B is the upper bound. It's all good and dandy. It'll return two values, it'll give you two values. So integral 0, like the zeroth, or like the 0th element, or the first value that it spits out is going to be like the actual result, and then the second value is the error on that result. So that's always great. It gives you the error on your integral as well as the actual value that it calculates. Because sometimes some integrals are really hard for the computer to calculate. They might need like super high resolution to be able to calculate it. And you want to be able to report how much error is in your calculation, right? So anyway, that's Gaussian Quadrature integral for a single variable. You can scale it up to a double integral, and it's double quad. It's the same thing. You have a function of x and y, or y and x, whatever. Your lower bound for x, your lower bound for y. I mean, your lower bound of x, or upper bound of x, and then g fun is like, that's short for like the lower bound of y. It has to be a function of y of x. If you haven't taken multivariable calculus, don't worry about it. You'll learn about that a little bit more, like why it needs to be a function of x in your classes. But for those of you that have had multivariable calculus, the lower bound has to be a function of y of x, and then the upper bound also has to be a function of y of x. And that's shown here, right? Yeah, so x1 and x2, since they're on the outside, they're the outer integrals, they have to be constant values. And then y1 and y2 need to be like functions of x. But yeah. And if you really, really want, you can go check the documentation, because the order does matter here. But yeah, I mean, it's just a couple more arguments in the function that you have to worry about. But if you're curious, that's how you do a double integral. And here's an example, right? So I define a function. I guess it needs to be y then x in your arguments, but I'm pretty sure it could be x comma y. But if I remember right from last semester, it actually does matter. So anyway, function of y comma x. Let's just do x times y. That's a good, nice and easy function. We're going to use our double quad function. You plug that in. We just use the normal way, but if you wanted to, you could use a lambda function here, like how I said earlier. And then our bounds are 3, 6 for the x integral, and then for the y integral, it goes from 1 to x squared. And this is a good case of like when you would want a lambda function, because it'd be kind of a pain in the butt to write like definition or like def, like just some stupid name, and then it only returns the number 1 for a given x, right? So it's easier just to write a lambda function saying, hey, for every single x value, spit out a 1, right? For every single x value, spit out x squared. That's a pretty easy bound to work with, and it's short. It's like a one-liner. You definitely don't need like a whole body to do it. So that's when you would use a lambda function. Usually is for like bounds in a double or a triple integral. And you could do this for a triple integral. It's the only difference is you have another set of function bounds. You have a TPL instead of a DVL for your double integral. And remember, this will spit out the value of the integral as well as the error on the integral. But that's, I mean, that's numerical and, that's numerical differentiation integration for you. It's pretty straightforward, just like these two functions and just knowing how to use them. Oftentimes you'll come across errors. It'll like spit out, hey, I don't know how to do this, or blah, 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 there's an error. Usually you just copy and paste the error statement into Google, find somebody who figured it out on their Stack Overflow, and then you see what they did, and then it helps you do your problems, or come to office hours. I prefer if you come to office hours and we can help you. But yeah, I mean, that's kind of how it goes with numerical differentiation integration. Not that much to it. Is there any questions about all of that? I guess my question to everybody would be, would you like to see a example of like me using like the function, like the integral in different like derivative functions, or would you prefer to get out 10 minutes early? I'll give everybody that option. Okay. Since somebody did say examples, we'll go ahead and do an example. If you feel like you're good though, if you feel like you don't need an example of how to do this, you're free to leave. But if you want to stay for like a couple more minutes, I'll go through an example on Jupyter Notebook. But yeah, so let's go ahead and do that. Really quick, let me just remember the name of the library. So I put out MISC import derivative. Yeah, so let's go ahead and do that. Oh, here we go. So we'll go to the Scipy, the miscellaneous part of the Scipy library. So scipy.misc, and we only care about the derivative function from here. So we're going to import just the derivative function with the syntax. So now we have the derivative function, and we can work with it. I'm going to define a basic function. We'll just call it f of x. Okay. And we're just going to say, I mean, we'll just return x. We'll return sine of x. How about that? Well, yeah, we'll return sine of x. And remember, we imported NumPy last time, so we don't have to worry about importing it again. And then let's just go ahead and try calling it. So if I remember right, it takes in derivative, takes in the function, and then takes in x naught. Let's just evaluate it at what the sine of 0 is 0, and the derivative is a cosine. So yeah, let's evaluate it at 0. So it should give us like a plus or minus 1. I believe it's a minus 1. And then the dx that we care about, we can just set that equal to like 1e negative 6. That's the same thing as 10 to the negative 6. It's just shorthand for that. And then I don't think there's any other arguments. Oh yeah, the like the number. We'll just calculate the first derivative. And that'll be like, dx. No, we'll just call it y. So if we go ahead and print y, positional argument. There we go, n equals 1. So you get 0.9999. I mean, there's a little bit of error on there, but if you decrease the, or if you make this smaller, it gets closer and closer and closer to the actual value. And then if you wanted to calculate like a whole list, I think you could just actually, let me try something. I don't remember if this is exactly what you can do, but if you make like a linspace from, I don't know, negative pi to pi, say you give it 100 values, we'll call that x. If you go ahead and slam that right into the derivative function in place of x naught, right? So this was x naught, this is 0. That's where we're evaluating. I believe if you just plug in a whole array, it'll do this for the entire array. Yeah, let's go ahead and print y. Yeah, cool. So now that I know that it works, we can go ahead and plot it, right? Import matplotlib dot pyplot as plt. Go ahead and just move that up here because I don't want that. And then if you just and then plot dot plot, we can go ahead and plot x comma f of x, right? And then we can also plot x comma y, and that'll be like the derivative. And we'll just, for clarity, the original function sine of x will be red, and we'll turn the derivative blue. And you see we get a sine graph and a cosine graph. And similarly, if we wanted to, we can actually we can calculate higher order derivatives. So if we wanted to, y could be the second derivative, and then you get, what is it? So if you have sine of x, derivative of sine of x is cosine of x, and then derivative of cosine of x is negative sine x. So it should give you the negative graph of sine x, and so on. So that's how you work with this derivative function. And then we have 5 minutes left. And then we could do integration if we so chose. Yeah, I mean, why not? So we'll just do a plot.show to close that out. And then if you want to see integration, we'll just use the same f of x, but now we need to import, or we can use from scipy.integrate. We're going to import the quad function, and then we're just going to use y integrated. It's going to equal quad. It takes in f of x, and then it takes in what, a and b, I believe. So, or let me check the syntax. Syntax is going to be, where is it? Here it is. Just a function in a and b. Cool. Yeah, so a comma b, we can just set that from, I don't know, negative pi dot pi to np dot pi. That'll just integrate it. The bound, a bound is negative pi and the b bound is pi. And it'll give you this, which spits out nothing. But if we want, we could see, we could print the actual value, and then you can print the error on that value, like so. And then at the bottom, you see the integral, like the area under the curve is 0, which makes sense. If you integrate what, sine from negative pi to pi, that should give you 0. And then if you see the error, it's 10 to the negative 14, which is great. Of course, if you try it with other different functions, like, I don't know, I think like there's like one with rectangles, there's one with like Simpson's rule, and so on. This error, you'll see that 10 to the negative 14 is like far better than like any other function. And you don't even have to specify like your dx. Like it doesn't even really need your dx to figure out the best way to calculate your integral. But I mean, those are your examples of calculating integrals with scipy and derivatives with scipy. Oh, if you wanted to see what y underscore int is, just it's an array or a list, or I guess it's technically a tuple. My bad. So it just gives you like a tuple where the 0th index is the value, and the second or the first index is the error on that value for a given integral. Cool. Yeah, I mean that's everything I got for you today. We're done with a couple minutes early, so thank you everybody for coming. Please fill out the form. Don't forget, fill out your quiz form, survey form for the final projects. We need those done. But yeah, you're free to go. Have a good weekend or rest of your week.
Thank you.
I'll go ahead and stop recording.